This video goes with the Beers Law simulated lab from the Phet simulation website. The link is in Google Classroom and it takes you to this page. There's also this paper that goes with it. If you're able to print it, great. If you're not able to print it and you just want to look through, that's also fine. Okay. And you don't have to be able to see everything that I write down or everything that I do or be able to read all this print. You just need to be able to understand it and follow along. I'll go over this side of the paper and then we'll also do the simulation over here. Okay. So we'll go ahead and get started. Pull the simulation up and I'm going to go ahead and go full screen so you can see that. Okay. And come on. There we go. All right, so Beers Law. Did you know the amount of light transmitted or absorbed varies depending on the substance? And that's the basis of Beers Law. That's kind of the basic part, is that as light passes through a substance, a solution, that it will be absorbed and scattered as it travels through. And there's actually a way to calculate that. You don't have to worry about the calculation. We're just kind of looking at the effect of it. We're not actually going to do all the math that goes with it. We're just going to see how that effect goes through. Investigation question. What is the relationship between the wavelength of the light absorbed or transmitted, the solution concentration, and the path length? So what that's talking about is, what is the wavelength of the light? Basically the color of the light that goes through, how much of it gets absorbed, how much of it makes it through or is transmitted, how strong the concentration is of the solution, and how far the light has to travel through the solution. So that's the path length. That's how far the solution has to go. And here's where you would make a prediction. Okay. And I'm not going to tell you what to predict. This is for your own benefit. This is for you to think about. What do you think the relationship between the wavelength, remember we talked about wavelength and frequency and things like that, the wavelength and the solution concentration and the path length. How do you think those are all connected? Okay. So the lab procedure, we're going to compare 4 solutions of different colors. We're going to keep the path length at 1 centimeter for each solution. And we're going to set the wavelength to preset mode. All right, so we're going to move this over here so that way we can measure it. All right, and you see it's at 1 centimeter already. So we're just going to leave that where it is. And we're going to set the wavelength to the preset mode. So over here, the wavelength is set to preset, and we're going to leave that just like it is. Now this will give us information on how much light gets absorbed and how much light actually goes back out, the transmittance of the light. Our first solution is cobalt 2 nitrate. So we're going to switch to that. So cobalt 2 nitrate. And what is the color of the solution? To me, it looks red. So I'm going to put down red. Color of the beam. So I'm going to turn the light on. All right. And so here's the color of the beam, and it looks green to me. The wavelength is 549 nanometers, so 549 nm. All right, and the absorbance. All right, so we're going to switch this over to absorbance, and it says 0.47. So our absorbance is 0.47. And transmittance, 33.73%. Okay, so the color of the solution, the color of the beam, the wavelength, the absorbance, and the transmittance. Okay. All right, next one is potassium dichromate. So we'll switch to that, potassium dichromate. Okay, so there's some changes here. Color of the solution, this is kind of an orange color. And the light looks purple. And the wavelength, 300 at 92 nanometers. Absorbance is 0.37. Transmittance is 42.69%. 42.69%. Okay. Nickel 2 chloride is green, and the color of the beam is blue. The wavelength is 433 nanometers. Absorbance is 0.53, and transmittance is 29.44%. Last one, copper 2 sulfate. Color of the solution is blue. Color of the beam, that looks kind of brown. And the wavelength is 780 nanometers. Absorbance is 0.96. And transmittance is 10.94%. Okay, so we have this chart filled out. And now it's saying, how are the beam wavelength and the absorbance value related? So looking at these two right here, okay, I have a low number here and a low number here. And I have a high number here and a high number here. And I notice that it follows that pattern. As it comes down in wavelength, okay, the numbers pretty much adjust with the absorbance value. So I think the longer the wavelength, of the beam, higher. I'm having trouble with H's today. Higher H-G. Absorbance. Okay. So the longer the wavelength, these are much longer, the higher the absorbance. Okay. All right, so moving on, we're going to change the solution to potassium chromate. There it is. We're going to keep the path at 1 centimeter. Complete the table below for the transmittance and absorption for that solution. So we're going to drop that down to 0. Concentration is 0. So transmittance, 100%. And absorbance, 0.00. Now as you're doing this, if you get a little bit different number, this is a simulation, so the numbers may be slightly different, what you get over here than what I get over here. And that's okay. That's just part of how the simulation works. Okay. We're going to move this over. We want this to be 100. Okay, so 100 transmittance, we get 33.36%. The absorbance, 0.48. Now I move this to 200. Absorbance, 0.96. Transmittance, 11.08%. Now if you notice, as we start adding more stuff, less and less light is making it through. More and more is getting absorbed. Yeah, so At 300, we only get 3.71%. And absorbance, 1.43. And then at full 400 concentration, we only get 1.24%. The absorbance 1.91. Okay. So as we add more and more and more of the stuff in there, the less light gets transmitted through, the more of it gets absorbed. All right, now we're going to graph this, concentration versus absorbance and concentration versus transmittance. All right, so we have a concentration, okay, and our concentration at 0 was 0 on absorbance. Okay. Then our concentration at 100 was 0.48. That looks to be about right here. 200 absorbance is 0.96, so almost to 1. 300, 1.43. And then at 400, 1.91. Okay. Now we have a nice graph of this right here. And now concentration versus transmittance. At concentration of 0, transmittance is 100. Okay. And at a concentration of 100, it's about 33%. So that's 30. So I'm going to put it about right here. Okay. And at 200, it's at 11, so that's almost to the 10. And at 300, it's at 3.71, so just barely right there. And at 400, it's 1.24. All right. So this is a much different graph. All right. So here we have that nice straight line, and here we have a curve. So what does this tell you? Which one is inverse and which one's direct? Concentration has a direct relationship with absorbance. The higher the concentration, the more gets absorbed. Inverse is the other way around. The higher the concentration, the less gets through. As the concentration drops, more goes through. Okay. So concentration and absorbance are concentration and absorbance are directly related. Concentration and transmittance are inversely related. All right, so number 7 says keep the solution set to potassium chromate, increase the path length to 2 centimeters. So we're going to make it even thicker. So we're going to crank this up to 2. There we go. Okay. And now complete the table for the transmittance and absorption for that solution. All right, so we'll drop the concentration all the way back down to 0 again. We have transmittance of 100% and an absorbance of 0. Increasing the concentration to 100 gets us an absorbance of 0.96 and a transmittance of 11.09%. Concentration of 200 gets us 1.25% and an absorbance of 1.90. Concentration of 300 gets us an absorbance of 2.86 and a transmittance of 0.14%. And then full concentration of 400, 0.02% transmittance and absorbance of 3.82. Now I'm going to pull this other paper back over here. So you can see a difference in the numbers just by making it longer, more of the stuff to go through. It definitely changed the numbers, whereas here it was 100 got us 11.9. When there was less to go through, it was 33.36. So now we're going to graph again. Now be careful because this is swapped. Last time it was absorbance and this side was transmittance. And this one is the other way around. Okay, so here we see concentration of 400, transmittance of 3.82. So that's way back over here. Excuse me, transmittance of 0.02. That's way back over here. All right, concentration of 300. When we drop that down, it's 0.14. It's still really, really small. 200 comes up to 1.25. Coming out a little bit. 100, it goes out to 11.09. And then at 0, it goes all the way over here. So there's that curve again. Right. Concentration and absorbance. At 0, we have 0. At 100, we have 0.96. At 200, we have 1.9. At 300, we have 2.8. And at 400, we have 3.82. Okay. So number 9, what changes did you observe about transmittance and the absorbance when the path length was increased from 1 centimeter to 2 centimeter? Okay. So again, we see a lot more light gets through whenever there's a lot less of the stuff to kind of block it, to kind of absorb it. So whenever we shrink this, you can see that absorbance number go down. And the transmittance number, got the wrong thing, go up. Okay. So when the path length was increased, then that caused transmittance decrease. Oh, not transmittance decrease and absorbance increase. Okay. And that makes sense because there's more stuff in the way to get absorbed, more chances for things to pick up that beam of light and to keep it from being able to travel all the way through to the end. Now, according to Beer's law, there are factors that determine the amount of light that passes through a solution. Identify two of these factors. The main two that we messed with on this was concentration and path length. But we also talked about wavelength as well. And so that was kind of a walkthrough of the Phet simulation of Beer's lab. And if you have any questions, please contact us through Google or email us. And I hope you guys are doing well.